All right, I think we're ready to go. Welcome to day 21 of assembly language class. We've got about 3 weeks left in the semester, and we're going to be covering a few topics that we kind of skipped over previously in the semester, or that we were able to leave out until this point. And we got a couple. We've got, of course, you turned in the RLC homework today. You have another week if you need to take advantage of the late deadline for that, although it'll cost you a few points. We've got the ARM assignment due next Wednesday. I spent a little bit of time trying to figure out different ways that you could run ARM sim, and I updated the instructions for that, so be sure to have a look. If you're on a Windows machine, it should be pretty easy to run ARM sim. If you're on a Linux machine, it should be still pretty easy, but a little trickier to run ARM sim. If you're like me and you do most of your work on a Macintosh, ARM sim will be harder to take advantage of. But in the instructions, I list some alternatives that you have for that, which will mostly be in using a virtual machine, either one running on your laptop or one provided by the university. You still have a week and a half to get that done, but you might, especially if you're coming from a Mac, you might want to get started early on that one. And then after that, we've got 2 more programming assignments, and then I think that's it for the semester, except for our final exam. Speaking of exams, we have, you took as you know, took an exam last week. I think all the questions were auto-graded by Moodle. So your grade ought to be available already for that. If you think a mistake was made, or you think one of the questions was graded incorrectly or unclear, I normally ask the regrade requests to go straight to me. So just write me up an email explaining what you think was done wrong. Send it to me, dbsturgey@ncsu.edu. And be sure to put regrade in the subject line. I normally look for that when I'm looking for regrade requests, so that'll help make sure that I don't miss that. That was administrative stuff. Any questions or about that, or any other questions before we get started with today's material? All right. So I mentioned we got 3 weeks of class left, I think, and we've got a few topics that we've only touched on a little bit so far this semester, and this is one of them. I know in 2 lectures we talked a little bit about microcode. And I felt a little bad trying to explain that because I knew we didn't have enough examples for that to make complete sense. We probably spent most of our time talking about microcode when we were talking about alternatives for implementing multiplication. And we said we kind of convinced ourselves we could build using gates, like and or gates that we talked about. We could build a little circuit that did multiplication. But for multiplying non-trivial numbers, it might take thousands of gates to do that. So we looked at microcode as a way of implementing machine instructions as a series of steps, almost like some machine instructions might involve executing a little process. And we talked about what that process might do during that lecture, but we didn't really talk about how it might work. And that's what we're going to try to fill in today. How could microcode work? How could we write a little low-level program, in a way even lower than machine language level, that does what each of the machine instructions says, that decodes the machine instruction, makes sense out of it, and executes a series of steps. For really simple instructions, maybe that's only one step. But for trickier, more complicated instructions, it might be a sequence of steps to do what that instruction says. And that's what microcode is made to do. This is a picture of what, I think it's a 68,000 processor. This was a 32-bit processor that came out in the early 80s. I think it was the first processor that ran the Macintosh, than desktop machines. And this shows kind of what the regions of the processor were dedicated to. And you can see there's a chunk up near the top that you can read as micro ROM. That little kind of U in front is the prefix for micro. And that is where, so this processor, the 68,000, was built kind of like the x86, or sorry, the 8086. We talked about it a little bit before. And it was designed as a 32-bit processor, but it was a CISC processor like the 8086, meaning it had a variety of instructions of complicated, some of them complicated instructions. And implementing these instructions was simplified by having a little program right on the processor that said what each instruction did. And here we can see that. This is, at least we can see a little block for that. This is the sequence of instructions that are this part of the processor contained the micro instructions, the sequence of instructions that controlled the processor for each machine instruction. So the machine language instructions we write would be implemented within the processor using a little program in this micro instruction ROM. We've already said some of the stuff, much of the stuff on this slide. So you'll remember micro programming is the idea that every instruction might be implemented via a little program, a program that's internal to the processor. So a sequence of really low-level machine instructions that that do the various steps needed to do that instruction, using micro instructions that we don't have programmatic access to. So even as a machine language programmer, we can't run individual micro instructions. We write machine language instructions, and then within the processor, any one of those might be implemented with one or more micro instructions. As we'll see, each micro instruction is kind of a very low-level step that might say things like, read this thing from memory, add these two registers together, write this result out to memory. So kind of a sequence of instructions that does what each of our machine language instructions says. The idea of breaking an instruction down into multiple steps is something that we're already pretty good at as computer scientists. In a higher level language, you might think of calling the square root function, and you might think of that as a single step in your program, even though you know that computing the square root might call a subroutine, or it might execute a machine instruction that does that computes the square root in multiple steps. Dropping down a level, if you're programming in machine language, if you ask to do a multiply operation, then that, depending upon your processor, that multiply might be implemented as kind of like a subroutine call, as a sequence of these lower level micro instructions. And that's what we talked about a couple of lectures ago. I guess a nice thing about microcode is it gives you a way of implementing complicated instructions as a sequence of steps rather than having to build a circuit that knows how to multiply any two 16-bit numbers. You could build a little micro program, a little sequence of really low level instructions that knows how to do the multiply operation without having to build a lot of hardware to do that. And that's kind of what we talked about when we talked about this previously. Changing the microcode in a processor might let us get a processor to emulate some different processor. We could change the instruction set that it supports, or change how that instruction set is implemented, change what we do when a particular machine instruction comes along. And that could, again, it could let one microprocessor masquerade as a different one. It could let us improve performance if we figure out a better way to do a particular operation. Or it could even let us fix bugs if we detect after a processor has been released, if we detect that one of the instructions is not doing what it should, or that it's it's computing the wrong thing. under some special cases, then changing the microcode might be something we could do without having to swap out the processor for that machine. So we're going to make up a pretend processor. It's going to be a little smaller than the 8086 and a lot simpler to decode instructions, but it's going to be enough to let us see how microcode could work. And you could see the microcode that's used inside of an 8086 as an extension of the ideas that we're talking about here. So what's our pretend machine going to look like? What can we build that shows off microcode, but is simple enough that we can kind of understand it? So we're going to pretend that we have access to a small memory, 256 bytes in total. The reason for picking that is then a single 8-bit quantity could pick any memory address. So that's the reason for the tiny little memory. I guess we're imagining that this could be a processor that could run on some embedded system that might control a vending machine or a washing machine or something like that, somewhere where 256 bytes of memory would be enough for that application. Again, this is just made up, but it shows off what might be typical of a micro-programmed processor. So we're going to have access to, again, 256 bytes of memory. You're going to have 2 registers that you can work with as you're computing. One that we'll call an accumulator. This will be kind of like the AX register on the 8086. And to tell you the truth, I was writing assembly language at about this time, just a little bit of it. But the idea of a processor with an accumulator, or whether it was the 8086 or some other processor, kind of having a main register that you did to do work, that was a common idea at the time. So we'll have an accumulator. It'll be an 8-bit register. We'll also have what we'll call an index register, and that'll be kind of like, I guess, the SI or the DI register on the 8086. We could use that to index through memory to read or write a byte, and then move on to read or write the next byte. At least that'll be kind of the intent behind that register. We'll have machine instructions that'll be in 2 formats, and that's what's shown at the bottom of this slide. So we can have some 1-byte instructions where there's just an opcode. So that'll give us 256 different 1-byte instructions. So that 1 byte will have to specify what we want to compute, like add or subtract or read or write a piece of memory. And it'll have to specify what register we want to work with. And that will assume that in some way that's all encoded in that opcode. Not every, we might want some instructions that have other operands, like an instruction that accessed some, or that used some immediate data, or an instruction that accessed a particular location in memory. We'll pretend those take 2-byte formats. So still a 1 byte for the opcode, but for instructions that need an immediate value, we'll pretend we can have a 1 byte immediate value that comes after the opcode. Or if they need to access memory, they can have a 1 byte address that comes after the opcode. And that all works out nicely because we're pretending we just have 256 bytes of memory. So any address would fit in that 1 byte operand. And if our registers are 8 bits, and we're pretending that, I don't know if I mentioned it, but it's a couple of lines up there, we're pretending our registers are 8 bits apiece. So any immediate value that we might load into a register would also fit into an operand. We got some examples of instructions we might expect. And the reason I'm introducing this, we're not going to program in this assembly language. We don't have an emulator for it or anything like that. But we're going to think later about how we might implement instructions like this in microcode. So we're kind of thinking ahead to, well, what instructions might we want? So over on the left, we've got some examples of 1-byte instructions. Like we might want an instruction to clear the accumulator, or increment the index register to move ahead, say, to the next byte of memory, or decrement maybe either of our registers, or add what's in our 2 registers and store the result in one of them, or subtract. So over there on the left are just instructions that operate on registers. They don't have to access memory or immediate values. If we want that, if we want to access memory or if we want an immediate value, that's going to require one of these 2-byte formats that we're pretending we have. The opcode we'll count on, or we'll design the instruction set so that fits in a byte. And then the operand could be a memory address, like in that first example, loading a byte from memory into the accumulator. Well, the part of the instruction that says load this thing into the accumulator, that would be in the opcode. And then the location of memory that we're trying to load, that would be in the operand. Or adding a memory location to one of our registers, or adding an immediate value to one of our registers, or subtracting a location of memory from one of our registers. Those would be examples of the 2-byte instructions we might want to compute. We're going to need access to some numeric constants, and we're just thinking here, we're thinking ahead to how we're going to build this microprocessor. What does it need to be able to compute? And things like that clear accumulator instruction, if you let me back up a slide, that was the first one we said, well, let's pretend we might want an instruction like that. That's going to need access to a value of 0 somehow. We'll need a bunch of 0 bits to do that. Things like incrementing or decrementing. We're going to need a constant of 1 to do that. And it's worth thinking about, well, if we were building the hardware for this processor, where are these constants going to come from? Especially, essential constants, like if we need a value of 0, if we need a value of 1. So to have these constants, to have access to these constants and the 2 registers that we talked about, we're going to pretend that our processor has 8 internal registers. And 2 of those are going to be the ones that we talked about a moment ago. Those are the ones that are in orange here. So, and they each, we've got 8 of them, so that's a nice round number in binary. And they each have a name, a human name, like accumulator or the index register, but they each have a numeric identifier that's listed over there on the left. And that's where 8 ends up being an important number, because if each of our 8 registers has a binary identifier, then it takes 3 bits to specify those. So like it shows kind of at the bottom of this chart, 101, and you'll get to see this chart over and over, so you don't have to memorize these or anything, but we'll have a identification like 101, that'll identify the accumulator. 110, that'll be that other index register. So these are the registers accessible to the programmer. We'll also have some other registers for doing internal work in the processor that aren't even accessible to the programmer. They're hidden inside the processor. And that's what, we said we're going to have 8 registers, each of them 8 bits in capacity. 2 of them are going to be programmatically available to the assembly language programmer. The other 6 are for internal use. That's how the microcode is going to work. And some of these are no surprise. Like that first one, 000, that's the program counter. I said 000, that's its numeric identification. That first register just keeps up with the location of the next instruction we're going to run. This is not a register that the programmer can, at least we're pretending, It's not a register the programmer can directly work with, even in assembly language, but internally, we're going to need to keep up with the next instruction that we're going to run. So we'll pretend that's the location of the next instruction. Our instructions themselves, we said they're either going to be 1 byte or 2 bytes. And after the processor goes and gets them out of memory, it needs to be able to look at them. So we're pretending the next 2 registers are just for holding the contents of the instruction. If it's a 1 byte instruction, then just the first instruction register, the 001 register, is enough. But if it's 2 byte, if it also has an operand, we'll pretend when that instruction starts executing, it gets loaded into the operand part gets loaded into that second instruction register, the 0101, the one named 010. The next 2, well, they're not really for storing things, and we won't be able to store things in them, but they're going to be for getting those 2 constants that we just talked about. We said, well, for some instructions, it's going to be handy to say, give me a byte worth of zeros. Well, we're going to have a register that we pretend holds nothing, or its only job is to have 8 zeros, 8 bits worth of zeros, so a byte worth of zeros. That's that constant 0 register, the one at identified by 011. The next one is going to be for a constant of 1. And the last one is going to be for scratch space during the execution of a machine instruction. That's the one called micro work, or it looks kind of like U work register down at the bottom. We can use that internally as we're figuring out how to implement micro instructions. So I guess a thing to notice is out of our 8 registers, we spent 2 of them, not really to store things, but just to have easy access to the constants 0 and 1. So we're kind of, again, what are we doing here? We're trying to design a pretend CPU that has enough complexity that we might want to use microcode for it, but is simple enough that we can, we don't have to be too sophisticated in designing the hardware. Questions before I can try to move on? All right, so this is kind of the storage we have access to as our pretend processor is running. Well, we better be able to do something with it. So we're going to pretend that each of these registers can provide its value for some kind of computation, and it can get a new value that's the result of a computation. We'll imagine that each of these is each of these is done by a bus. So, and that's what this picture is trying to show. So the A bus can get a value from either the program counter or the first part of the instruction, or the operand of the instruction if it has one, or it can get its value from constant 0 or 1, or the accumulator, or the index register, or the scratch space register. So that's what this part indicates. Same kind of thing for the B bus. So we got a separate bus, and it can get its value from any one of these registers. What do I mean by get its value? Well, we're going to build hardware using gates. We're not going to do that today. We'll save that for the electrical engineer types. But if you were taking this class at a little bit lower of a level, you could see how to build a series of gates that does what these buses talk about doing, that lets the B bus get its value from any of these 8 registers, or lets the A bus get its value from any of these 8 registers. Same thing on this end, and I don't think I said this before, but we're going to have a third bus, we'll call it C, that can provide a value, the result of some previous computation, And then we can choose to store that value in any of these 6 registers. We left out the 2 constants because, well, if this register 011 is always supposed to be the constant 0, then we don't want to store a different value there. Its job is going to be to always be able to give us a byte worth of 0 bits when we need it. Same thing for the constant 1 register. So we can't store a result in those, but that's not really what they're for. They're just convenient ways of getting these 2 useful constants. If we need other constants, and we'll see this later, we're either going to have to compute them in one or more steps, or we're going to have to store them somewhere in memory and get them out of memory. So I've tried to describe what these buses are for, but I haven't said what we're going to do with the values on them. I've probably said something vague, like we're going to be able to put a value on the A bus, we're going to be able to put a value on the B bus. Both of these buses are going to feed what we'll call the ALU, the arithmetic logic unit, or arithmetic logical unit. This is a circuit that knows how to do some basic computations, and we've listed them there. In fact, for this example, we're just going to pretend we have a few basic computations. The ALU can add 2 8-bit numbers. It can compute the bitwise AND of 2 8-bit numbers. It can ignore the B bus and just take what's on the A bus. That's the pass A that's second to bottom there. And it can ignore the B bus and just flip all the bits on the A bus. The output, so the ALU would be just the series of gates that we need to compute any one of these operations. And the ones that we've picked here are simple enough that it wouldn't take too many gates to implement them. Even a 8-bit AND of 2 numbers wouldn't take that many gates with propagating the carry through it. So the ALU takes input from these 2 buses. Based on some control bits, it knows how to compute any one of these 4 things. And then, like the picture shows, whatever the result is, we can use that a few different ways. That's what the C bus comes from. It's the result of the most recent ALU computation. So you can think of as this processor, this pretend tiny little processor that we're making up, as it computes. Steps in its computation are going to be reading 2 values, or I say 2 values, reading 1 or 2 values from these registers, doing an ALU operation on them, and then sending the result maybe to one of at least 6 of potentially one of these 6 result or registers. Sorry, I'm just trying to say one of these registers, except the 2 constant ones where you wouldn't want to change the value. Questions before I try to move on? All right, so the microcode is really going to tell this thing what to do. So when I say things like, oh, get the value, get the accumulator and put it on the A bus, and get the constant 1 and put that on the B bus, that's what the microcode will say. It'll say to do that. We've got a slide or 2 before we get to that. I guess the last thing to talk about is memory. It's not enough just to be able to access these 8 registers, but we also need to be able to read or write memory. So we're going to pretend there's an address bus and a data bus. And that's what these 2 arrows on the left indicate. The address bus, and these go to your memory. So we'll pretend we've got a 256 byte memory, and it's looking at the address bus to know which of those 256 bytes should be accessed. So this 1 arrow here, assume that carries 8 bits. 8 bits to indicate which address of memory is being accessed. And then the data bus is also 8 bits. It's the contents of memory. And we're going to assume that the data bus is bidirectional. So you can see We tried to indicate that in this picture. It's got a little arrow over here and an arrow over here. So that data bus can be used to read or write to memory. So if you want to get what's in a byte of memory on the address bus, we put the address that we want to access, the address of the byte we want to access, and then we look at the data bus to see what's in that location of memory. So we're pretending that however memory is implemented, it can see the address that's on the address bus. And if we're trying to read from memory, it'll provide the contents of that memory on the data bus. If we're trying to write to memory, it'll be the other way around. Address bus, well, sort of. Address bus will still say what address are you trying to access. But instead of memory providing 8 bits of data, it will read 8 bits of data from the data bus and store it at that location in memory. So again, we're pretending address bus is one directional. The processor says what location of memory it cares about. And data bus is bidirectional. If we're writing, it provides 8 bits of data. If we're reading from memory, it receives 8 bits of memory. And that is surprising. Oh, sorry, I should talk about these switches. So until this slide, we assumed that values just kind of rode around a cycle here. We'd get 2 values on the A and B bus. We'd run them through the ALU, and then they'd show up on the C bus, and they'd get stored in one of these 8 internal registers. But this connection to memory lets us also access memory, and these 3 switches let us control access to memory. Let me give an example that hopefully will make this more clear. We're assuming we have a switch S1 right here when I'm moving the mouse. And that controls whether the ALU as its A operand, as its left-hand operand, does it get one of the registers or does it get a byte from memory? If the switch has a value of 0, or if we set this switch to 0, it'll get the contents of the A bus. If we set it to 1, it'll get the contents of the data bus. So it'll get a byte from memory. Similar, let's go to the other end. Switch 2 is same idea, but for the writing end. Once we've computed something through the ALU, if switch 2 is set to 0, then that result might get fed into one of our registers. If we just computed something and switch 2 is set to 1, then that result gets fed into the data bus. So that's available for writing to memory. So because of switch 1 and switch 2, one of the inputs to the ALU can come from memory, or it can come from one of these 8 registers we already talked about. Because of switch 2, the result from the ALU can go to memory, can get written to a byte of memory, or it can get written to one of these registers. We just have one more switch. And that's for B. B can be used to provide the address of a memory location. So if we need to access memory, either reading or writing, then switch, I hope I worry that I said this wrong a moment ago. Switch 3 is for controlling the address bus. So if switch 3 is set to 1, then whatever's on the B bus gets fed to the address bus. That picks the location of memory that we're accessing, either for reading or writing. If switch 3 is set to 0, then the B bus goes straight into the ALU, and it could be used for one of the ALU computations. Questions before I try to move on? All right, so that's all of the moving parts that we need to control what computation happens. The micro instructions are what specify all of the stuff that we've been talking about. On this pretend processor, we're going to pretend a micro instruction is a 16-bit value, always 16 bits. So at the micro instruction level, every instruction is the same length. And it says what to do with all the hardware that we've been talking about. Let's, this isn't the first thing that we'll talk about, but as hopefully a good example, S1, this first bit, I guess this is kind of backward if you think of bit 0 as being the low order bit, then it normally it'd be over here on the right. But either way, bit 0 we'll pretend decides switch 1, S1. So if bit 0 of the micro instruction is 0, that sets the switch to read the first input from the ALU comes from bus A. If switch 1 is 1, then the first input from the ALU comes from the data bus. And you can see they're not all consecutive, but the two other switches we just talked about are controlled by bits 3 and 4 of the micro instruction. Here in the middle, bits 1 and 2 control the ALU. We said a couple of slides ago, we're pretending the ALU has 4 things it can do. It can add, it can compute the bitwise and, it can just ignore B and take a copy of A, or it can flip all the bits of A. Those are 4 operations, so we'll pretend whoever built the ALU built it with logic so that which operation it computes is determined by these 2 bits. In fact, here are the codes for that. If ALU, if bits 1 and 2 are 0, 0, then the ALU will add. Otherwise, it'll compute, if bits 1 and 2 are 0, 1, it'll compute the bitwise and. If they're 1, 0, it'll just take a copy of what's on A and ignore B. If they're 1, 1, it'll flip all the bits in A and ignore B. And when we say it will do this, well, that could mean it computes one of these 4 operations, or it could just mean what goes out on the C bus. Maybe it's got logic to compute all 4 of these operations all the time, and these 2 bits just determine which value makes it out. So if the ALU bits in the micro instruction are 0, 0, maybe it's the result of the add computation that gets put out on the C bus. And if this class was a little bit lower level, we could easily look at what it takes to build a series of gates that makes an ALU that can compute any 4 of these operations and that is controlled by a 2-bit quantity that picks the operation it computes based on these 2 bits. Questions before I try to move on? All right, so this is what a micro instruction looks like. We said it was 16 bits, and we're kind of talking through what each chunk of the bits is responsible for. And officially, this is the part we've described so far. Bits 1 and 2 tell the ALU what to do. So imagine that means when we're doing this 16-bit micro instruction, these 2 bits, whatever's in them gets fed straight into the ALU, controlling what operation it computes. All the bits at the end, bits 7 through 15, control what the buses do. And we talked about this initially. We said, pretend the A bus can get its value from any one of these 8 sources. Now, these 3 bits control which source it gets. So bits 7 through 9, if they say 0, 0, 0, then the A bus will get its value from the program counter. If they say 0, 0, 1, the A bus gets its value from the instruction register. I'll just do one more. If they say 1, 0, 1, then the A bus gets its value from the accumulator. And if we were building this hardware, when we were executing this particular micro instruction, these 3 bits would get fed into the circuit that selects the input for the A bus. So it'd be controlled directly from the currently executing micro instruction. These next 2 will go by faster. We're assuming the same thing for the B bus. So the next 3 bits, bits 10 through 12 in the micro instruction, says which of these values is on the B bus. And the last 3, bits 13 through 15, decide where the C bus goes. So if they're, for example, if they're 110, then whatever's on the C bus is going to get stored in the index register. Notice that there's a little wasted space in the micro instruction. We already said you would never want to try to store something in constant 0 or constant 1, but we're still spending 3 bits for that, for the where the C bus goes. We would just never really use a micro instruction that had 0, 1, 1 or 1, 0, 0 as bits 13 through 15, because that would say store what's on the C bus in one of these 2 constant registers. And we already said there's no point in doing that. You would never want to change the value of those registers. So there are some potential micro instructions that we would never actually use. Any micro instruction ending with 100 should never show up in the microcode for an instruction. So we've talked about most of what shows up in this micro instruction. I guess the part we haven't talked about too much is accessing memory. We talked about this a little bit, but we've got some pictures to help describe this. So we're assuming that the CPU can access memory for reading and writing machine language for a program, for reading and writing data that's being used by the program. And we've kind of already talked about this at a higher level. What does this mean? Well, for accessing memory, it's got an address bus that provides, that tells memory what address it wants to access. Here we're assuming that the address bus is 8 bits because our memory is only 256 bytes, so 2 to the 8th bytes on a realistic machine, on a modern general purpose computer. The address bus would be way wider than that. So if you're using a machine that has 8 gigabytes of memory, then you've got at least a 32-bit address bus just to specify all those 8, sorry, I said that wrong. I think I said an 8 gig machine, and I probably should have said, if you've got a machine with 4 gigabytes of memory, then you've got at least a 32-bit address bus just to access all 4 gigabytes of memory. I'm hesitating because I also worry that I said gigabit a moment ago, and I should have said gigabyte. Let me say it again, and I'll try and get it right this time, and I'll try and say it fast so I don't waste your time. So I was trying as an example to say, if you've got a machine that has 4 gigabytes of memory, that's about 4 billion bytes, you would need 32, at least an address bus of 32 bits, just to specify the address of every possible byte in your memory. For this pretend made up simple computer, we only need 8 bits in our address bus. That would let us access 2 to the 8th memory locations. And for this computer, that would be 2 to the 8th bytes of memory, so 256 bytes of memory. Like we said, on a modern machine, you might have a 32-bit address bus, or really probably bigger than that on a modern machine. We've kind of moved on past 32-bit machines today. If you're on a 64-bit machine like most of us are, you typically can't access 2 to the 64 bytes of memory. No real machine today could possibly have that much memory. But you probably have an address bus that's bigger than 32 bits to let you access more than 4 gigabytes of memory. At the time that the 8086 came out, as you know, we were kind of in the transition between 16-bit address buses and machines that needed access to larger amounts of memory. So even at the time, the address bus for a general purpose computer probably would have been a good bit bigger than 16 bits. So the address bus is for telling memory which byte you want to access. The data bus is for getting bytes, the contents of a byte from memory, or for updating, for writing out the new contents of a byte. And we already said, so that would mean the data bus would have to be bidirectional. You could use it to read 8 bits at a time or to write 8 bits at a time. Not every step in a microprogram needs to access memory. Some steps are just going to compute with what's already in the 8 registers we're pretending we have. So we're going to need part of the bus that just does control, that says to memory whether or not it can take a short break or whether or not it should pay attention to what's on the address bus. So we'll assume there's one more bit that's written to memory, or one more bit in our control bus that tells memory whether or not it needs to access its contents. If that bit, and we'll call that the address valid bit. If it's 0, that means don't even bother looking at the address bus. There's nothing on it, or we don't care about memory at this step. If it's a 1, that means pay attention to the address bus, because that's the byte of memory we're trying to access. So we're going to need one more bit, part of a control bus going to memory, again, that says whether or not it can take a break for a moment or if it needs to access its contents. And we already said we need to be able to read and write bytes in memory. So we're going to need another bit in the control bus that says that. The read-write bit, if it's a 0, we'll pretend that's our way of telling memory we want to do a read. So tell us, the data bus should tell us what's in a byte of memory. I hesitated, I should have said if the read bit is 0, that's telling memory to put the contents of a byte on the data bus. So set each of the bits of the data bus to match what's in 1 byte of memory. If it's a 1, then that's telling memory to change what's in a byte of memory. It's telling it, we've already put, the processor has already put 8 bits of data on the data bus, and you need to update a byte of memory to hold that. And when I say a byte of memory, I mean whichever byte is indicated by the address bus. So the address bus says what location of memory we care about, and the data bus is for reading or writing the contents of that memory. That being said, we can explain these two kind of middle bits in the micro instruction. Bit number 5 is the address valid bit. We're pretending whatever its value is, 0 or 1, goes straight to that control bit we were just talking about. And bit 6 is the read-write bit. So in a micro instruction, if it's 0, that's going to tell memory we want to read from a byte of memory. If it's 1, that's going to tell memory we want to write to a byte of memory. That, again, we've got a little bit of redundancy here because bit 6 doesn't matter if bit 5 is 0. Bit 5 is the address valid bit. I hope I said this right a moment ago. If it's 0, that tells memory we don't care. If it's 1, that tells memory we want to access the byte at a particular address. Well, if it's 0, then the read-write bit doesn't matter. We're not going to read or write memory if we've told memory we don't care, that we don't need to access it for this micro instruction. So that would also be a case where we've got potential micro instructions that we would never actually use. Questions before I try to go on? All right, and then I jumped ahead and mentioned these earlier. We've got slides for them here. The last 3 things are those 3 switches we talked about. So 3 bits in the micro instruction determine whether or not the ALU is accessing memory or is it accessing the contents of one of these 8 registers we talked about. So for instance, if they were all zeros, if bits 0, 3, and 4, or the ones we're calling, the ones that determine switch 1, 2, and 3, if they were all 0, then whatever's on the A bus would go into one of the ALU inputs. Whatever's on the B bus would be the other ALU input. And whatever got put on the C bus wouldn't go to memory. It would potentially go into one of these 6 registers. If we set them like this, if switch 1 was a 1, switch 2 was a 0, and switch 3 was a 1, well, a 1 in switch 1 would get the first ALU input from memory, from the contents of memory. For accessing the contents of memory, then we better provide an address. And the only way this processor can do it is if S3 is set to 1. So S3 better be a 1 to specify what location of memory we want. We can get it from any of these 8 places, but S3 being a 1 feeds the value of the B bus into the address bus. And then if we're reading from memory, we better not try to write memory at the same time. So switch 2 better be a 0 in this case. And again, when I say it better be this way, I'm kind of describing legal micro instructions versus ones that we would never actually use. We would never set S2 and S3 at the same time because we can't read and write data from memory at the same time. If we did want to write memory, here's what it would take. The only way to put something into memory is by putting it on the data bus. So we're going to have to set switch 2 to a 1. If we're writing to the data bus, we don't also want to read from it. So switch 1 would have to be a 0. And we've got to provide an address. So switch 3 would have to be a 1 in that case. So instructions that read from memory would look like over on the left, these blue values, they would have 1, 0, 1 in these 3 bits. Instructions that try to write to memory would look like 0, 1, 1 in those 3 bits. So this is what we've got to work with. Each micro instruction that kind of controls all of the control parts of this processor is a 16-bit instruction. And like we started with, if you looked at a micro-programmed processor, little sequences of instructions that say what to do for each machine instruction would be stored in ROM right on that processor. So this micro ROM box that we looked at earlier, you can think of that as containing all of the micro programs for all of the machine instructions. So for every instruction the processor can do, there's a little sequence of these 16-bit micro instructions that say, oh, if you want to do an increment of the accumulator, first you got to do this, and then you got to do this, and then you got to do this. And that's what this next slide is trying to show. So when it's time to do an instruction, we load, or this processor loads the instruction out of memory. Well, the program counter says what the next instruction is. It says where the next instruction is. So the processor can go get the contents of that instruction from memory. And we're kind of skipping over this part in our explanation, but getting that instruction would involve going and getting its opcode and storing it here in the first instruction register. And then if it has an operand, and that whether or not it had an operand would depend on the opcode. If it has an operand, then going and getting the operand from program counter +1 and storing that in the second instruction register. And then using the opcode to look up the start of a little micro program that says how to do that instruction. And that's what the right-hand part of this slide is trying to show. For each possible machine instruction, we're pretending there's a little sequence of micro instructions, these 16-bit micro instructions that we were just talking about, stored in, backing up a slide, stored right in ROM on the processor. And when you start running them, you'll execute each micro instruction. That means bring that instruction, or access the contents of that instruction, use each of its bits to control these parts of the microprocessor, and then move on to the next micro instruction until you reach the end of that micro instruction. That's what these ends are. We're pretending they're end markers for the microprogram. And then when you hit an end, you go get the next machine instruction, the next machine language instruction, and then load it into one or both of these two registers and start the process again. So running a micro instruction involves executing a little sequence of these 16-bit words. This picture is trying to show when you bring in, kind of what I said a moment ago, when you bring in the opcode for an instruction, that chooses the, based on what's in ROM, it chooses the start of the sequence of micro instructions for how to do that instruction. That gives you access, like the picture shows, that gives you the start of a sequence of these 16-bit micro instructions. And then for each of those, the 16 bits are choosing what value goes on the A bus, what value goes on the B bus, each of these switches, what operation the ALU needs to do, and so on. The only thing we've got left to do is to convince ourselves this could actually work. And we're going to do that by looking at some examples. Any questions before we try to look at what we might be able to do with this kind of processor? So we're going to go back to some of the examples we talked about earlier. We said, well, you might want a machine instruction that can clear the accumulator. We've only got these two orange registers that are available to the assembly language programmer. So we need, and we said it'd be nice to be able to clear to set the accumulator to 0. So if we're going to do that by running a sequence of 16-bit micro instructions, what would it take? There's a little picture here that shows, well, what does it mean to clear the accumulator? We just need to go get a 0 and put it in the accumulator. And this processor, it can't do a whole lot, but it's going to be really good at doing that because we've got a constant 0 and we spent a whole register just to have that whenever we need it. So if we could go get the contents of register 3, the constant 0, and just feed that back around as input to the accumulator, then our job would be done. And that's what this picture is trying to show. Just go get what's in register 3 and don't change it at all. Just put a copy of that in register 5. We say register 5 because that's the accumulator, register 101. What would it take to do that? Well, we need to go get constant 0. Part of our micro instruction specifies what thing goes onto the A bus. So let's just specify let's go specify register number 3. That's where the constant 0, we're assuming that's 8 bits worth of zeros whenever you need them. So the A bus needs to get its input from register 3. So we're kind of filling in this micro instruction as we go. So we need a micro instruction that says, go get what's in register 3. What do we want to do with it? Well, we don't need to get input from memory. We want to get constant 0. So switch 1 would say, well, just take the ALU input from the A bus, the constant 0 that we just got. Don't get that from memory. So switch 1 seems like it would have to be a 0. For the ALU, it does 4 computations, remember, and most of them were pretty simple. It can add, it can do a bitwise AND, it can just take the value of A and ignore the value of B, and it can take the value of A and flip all of its bits. We want that third one. We want to just take the value of A, and we're pretending that if we feed a value of 1, 0, we did this a few slides ago, that the ALU can do 4 different computations. And computation number 3, I say number 3 because I'm counting from 1 on that. I guess I would say it's computation 0 is to add, 1 is to bitwise AND, 2 is to just take A and ignore B, and that's the one we want. So that's 2 to tell the ALU what to do. So we're filling in this micro instruction gradually. For switch 2, once the ALU has, so we've got a constant 0, we didn't even need what was on the B bus. We passed it through unchanged. We don't want it to go out to memory, so switch 2 seems like it should be a 0. We want whatever that is to get stored in the accumulator, and the C bus determines that. So if we set the C bus to 5, that will take whatever, if we specify that the result on the C bus should go to register 5, then that 0 is going to go into the accumulator. And we're pretty much done. We got a bunch of bits in the micro instruction that we didn't even need. We're not accessing memory, so switch 3, and we're not even using the B bus, so switch 3 might as well be a 0. If we're not accessing memory, then address valid might as well be 0 because memory doesn't need to do anything. And we're not even using the B bus, so its value doesn't matter. In general, we'll assume that we can fill in zeros for bits that we don't need. In some places, that makes a lot of sense. Like we just said, if we're not even providing an address, the address valid bit probably should be a 0. And if we're not providing an address, then read write doesn't even matter. We'll assume it's okay to set it to 0. Since we're not using the B bus, the ALU is just taking whatever's on the A bus, we'll assume we can set it to 0. That means technically the B bus is getting the contents of the program counter, but the ALU is just ignoring it because we told it to just take what's in A. So here is the micro instruction. We just filled it in with zeros for the parts we didn't need. And that's all we have to do for clearing the accumulator. That instruction seems like it just needs 1 micro instruction. And that's what we'd like. We'd like, if we're trying to implement an efficient processor, we would like we'd like to be able to implement machine instructions with as few micro instructions as possible. So this one only requires 1. Questions before we try the next one? So this is just a sample of what we could do. We said we wanted to be able to clear the accumulator, and that's pretty easy. How about this? This is an add instruction that takes whatever's in the accumulator, goes and gets the contents of a memory byte, adds that to the accumulator, and just like 8086, stores the result in the accumulator. And this is going to take a couple of steps. We're going to implement this with help from, I mentioned this, we haven't talked about it too much, but you'll notice we've got some registers that are essential, like keeping up with where we are in the program and holding the contents of the current machine instruction we're executing. We got some that are visible to the program, so we better keep whatever the programmer wanted in those or whatever they left in those. But we've also got one that's just for scratch space, this microcode work register. And we're going to use that to implement this instruction. So this is what we're trying to do. And here's how we're going to do it. We're going to go get the contents of memory at whatever address we're supposed to access. So it's like going and getting the byte that's in this variable. And then we're going to add that to whatever's in the accumulator and store the result in the accumulator. And that's going to take 2 micro instructions, one to do each of those. We're assuming this instruction is encoded. I mean, it would be one of the ones that has to be encoded in 2 bytes, an opcode, and then an operand that says what memory location we want to access. So if we're going to go get the contents of some variable, that operand tells us where it is in memory. And when this instruction got brought in from memory, and I mean the machine instruction, the opcode went here in register 0 in the first instruction register, and the operand went here in the second instruction register. And that's what this picture is trying to show. So if we want to access memory, that's where we need to go. So the first part of this instruction, the first micro instruction, would say, take whatever's in register 2. That's this operand part of the instruction. Take whatever's in register 2 and go get that out of memory. So the B bus, that's the one that feeds the address bus if we need it. The B bus is getting its value from register 2. Switch 3 is sending that out on the address bus. So that's right here saying, well, let's tell memory that's what we want. And we better tell memory that it needs to pay attention. So the address valid bit needs to be set. We're accessing memory, so we're trying to get the contents of var. So we better set the read write bit to be read. That's what which we're assuming is a 0. So that's what this 0 here means. And we want to do something with that value. And the only thing we can do with it is feed it into the ALU. So switch 1 better be set to a 1 to get the ALU input from the data bus rather from this internal A bus. So that's got a lot of our instruction filled out. What do we want the ALU to do? It can compute 4 operations, but I don't think we want to do any math yet. We just want to get whatever's in, whatever comes from that byte of memory, and we want to store it in our microcode work register. So we better tell the ALU just to pass through whatever's on its first input. And same as the previous instruction, 1, 0 will tell it to do that. And then what do we want to do with it? Well, it'll come out on the C bus. We don't want to store it in memory. So switch 2 better be set to 0. And we need to save it temporarily. And we already decided, let's save that in our microcode work register. So the value of these last 3 bits determine that. So we'll say whatever's on the C bus needs to go in register 7 in the microcode work register. So we just did the first part of this instruction. I know it took some explaining. We got the contents of memory at whatever address was in the instruction, and we stored it in the microcode work register. We didn't need the A bus for this, so just like we did before, we'll assume we can set it to 0. Technically, it'll be getting the value of the program counter, but we weren't using it anyway, so that won't go anywhere. We're halfway done with this instruction, but now we have all the stuff we need. We need to take what we just got out of memory. That's, we just copied it to the work register. So let's put that on, oops, I misspoke. Well, we need to get that and we need to get the value of the accumulator. And the part I said wrong was the first operand. So for the first operand, let's get what's in the accumulator. So the A bus needs to get its value from register 5. That's this one right here, the accumulator. We want that to go straight into the ALU. So switch 1 better be a 0. We don't want to get a byte from memory. We want to use what we just put on the A bus. So that's part of our micro instruction. For the B bus, let's get its value from the microcode work register, the value we just read in from memory. So that's register number 7. We don't want that to feed the address bus. We want that to go in as the second ALU input. So switch 3 better be a 0. We're planning to add these two things together. So we better tell the ALU to do the add computation. I listed these a moment ago. We're pretending operation 0 is add, 1 is bitwise and, 2 is pass through A. So we'll tell it to do an add. That's instruction number 0. And then the sum of those will come out on the C bus. Well, we better not write that to memory because we don't need to. We better put that, at least according to this instruction, the result should go in the accumulator. So let's take whatever's on the C bus and put it back into the accumulator. And then we're pretty much done. We didn't need to access memory. So the address valid bit and the read write bit, those can both be 0. And then this should be all it takes to do this instruction. So adding the contents of memory to the accumulator and storing the result in the accumulator, it looks like the micro program for that is 2 instructions. We've got a couple of other examples. Let's see if we can get through at least the dumb version of one of these first. Questions before we try to move on? All right, how about a simple instruction like decrement the accumulator? I pretended that it was simple. It would sure be simple if we had a constant for a -1, or if our ALU did subtraction. But we don't have either of those. We're pretending our ALU only knows how to add. Well, we could get by with adding a 2's complement -1. We figured that out early in the semester. But we don't have a constant for -1 in 2's complement. We have a constant for 1 and we have a constant for 0. So we can still do this. We just have to make our own value for -1. And fortunately, we know how to do 2's complement. So we're going to implement this by creating a value for, sorry, I'm looking at these notes going away. We're going to do this by creating a constant for -1 and then adding that to the accumulator, and that'll be the same thing as subtracting 1. We're going to need scratch space to store our -1 constant. We could store that in the work register, the micro instruction work register. What does it take to compute, to create a -1 in the work register? Well, we know, and this is what I said a moment ago, we know how 2's complement works. So we could just take a 1 and flip all of its bits and then add a 1, and that would negate it. That's how you'll remember, that's how 2's complement works. And our ALU knows how to do all of that stuff. So that's what we're going to do. It's going to take a few steps, but we're going to take what's in our, we're going to take the constant 1. We've got a register for that. We're going to flip all of its bits, and the ALU knows how to do that. And we're going to store that in the work register. Then we're going to add 1 to it, which we can do because we've got a constant for 1 and the ALU knows how to add. So we can do that in our next micro instruction. And now we've got a -1. We can add that to what's in the accumulator and store the result in the accumulator. And then we did a decrement of the accumulator. This is going to take, like we just said, this is going to take 3 instructions. And if we looked at them in picture form, we don't have written out microcode for this, but it'd be easy to do. If we looked at it in picture form, we could go get our constant of 1, put it, we could flip all of its bits, and that would give us like, well, constant of 1 would look like this. 7 zeros and a 1. We ran it through the ALU and used operation 3. That would flip all of its bits. So that would give us 7 ones and a 0. And then to get a 2's complement -1, we have to add 1 to that. So we could run it through the ALU again, adding the constant 1 back to what was in the work register and storing the result in the work register. And this would take 3 instructions. Here we're kind of showing just here's how to get a -1. And even though there are 3 lines here, this would just take 2 instructions. In the first instruction, you'd get the 1 and flip all of its bits. And then in the second micro instruction, you'd add 1 to it. But we did all of that work just to get a -1, which in binary looks like this. We could have gotten that faster if we were more clever. If you just wanted 8 ones in a row, that's -1 in 2's complement, we could have just taken our other constant, 0, and run that through the ALU, telling it to flip all the bits. And that would have given us a -1 in 1 step. And that would have let us do decrement accumulator in 2 steps rather than 3 steps. So this over on the right shows a more efficient way to implement this. This slide doesn't show the full implementation, but over on the left, again, and I'll say this real fast because I'm past my time. Over on the left, we're proposing take a 1, flip all of its bits, and store it in the work register. That's 1 micro instruction. Add 1 to it, that's another micro instruction. And then add that to the accumulator and store the result in the accumulator. That's 1 more micro instruction. So that's 3. Over on the right, the more efficient way would be to take your 0 and flip all of its bits, getting a -1 in 1 step. That's 1 micro instruction. And then again, add that to the accumulator. That's 1 more micro instruction. So over here on the right, that's 2 steps, which would be, again, a more efficient way to do it than the 3-step version. We'll have to save these for next time, but if we look at some fancier instructions, we can find some of the same things. Clever ways of implementing instructions in microcode. And that's one of the advantages of microcode, is you can refine a processor potentially after it's already been released by changing the implementation of things based on either how people use them in practice or based on figuring out new, more efficient ways to do things. But that'll have to wait for next time. Let me go ahead and stop recording. And if you have questions, as always, hang around and I'll try and take your questions. Otherwise, I'll see you on Wednesday. Have a good week.